International Webinar Series,
This
Cognitive
conference
Computing.
will now be recorded.
A very good evening to all. I, Palak Sharma, welcome you all to day 3 of our 5-day international webinar series on applications of cognitive computing in the modern era in collaboration with International Centre for Free and Open Source Software, Government of Kerala. We owe a special thanks to today's guest speaker, Professor N. Sundararajan from Nanyang Technological University, Singapore. Professor N. Sundararajan received the BE in Electrical Engineering with first-class honours from the University of Madras in 1966, M.Tech from the Indian Institute of Technology, Madras in 1968, and PhD in Electrical Engineering from the University of Illinois, Urbana-Champaign in 1971. From 1972 to 1991, he was working in the Indian Space Research Organisation, Trivandrum, India, starting from Control System Designer to Director Launch Vehicle Design Group, contributing to the design and development of the Indian satellite launch vehicles. He has also worked as NRC Research Associate at NASA Ames in 1974 and as a Senior Research Associate at NASA Langley in 1981 to 86. From February 1991, he was working in the School of Electrical and Electronic Engineering, NTU, Singapore, first as an associate professor and presently as a professor, retired in July 2010. From 2010 to 2013, he was an emeritus visiting professor at the Indian Institute of Space and Technology, Trivandrum, India. We welcome you, sir. Over to you.
Can you hear me now? Can you hear me?
Yes, sir, you're audible.
Okay, let me share. First of all, good evening to all of you. Thank you for inviting me to give this talk. I have to thank especially Madam Dipali and the management for giving me an opportunity to talk to you all. So essentially the topic is some of the work we have been doing in this area for the last 5 to 7 to 8 years, and over a period of number of our PhD students and all. So what I will do is I give an overview, and then we can have a question and answer session at the end. But if you have any questions you want to interrupt, you can unmute and ask the question. That's fine with me. So we will start with that.
So we will have question answer at the end of the session.
Yeah,
we have other participants.
In between they can ask.
Okay, sir.
No, okay. Very rarely they can ask. I agree with you. I mean, so
okay.
We will. If you have any questions, you please keep it. We will discuss in the end. But if something is very important you want to ask, you can interrupt. I don't have a problem. So long as the network is fine, everything is okay for me. Okay, let me get into the problem first, the talk first. I had to share, right? Let's see. Are you able to see my screen now? Sorry.
Yes, sir.
Yes, sir. Hold on. I had to go to the first slide, not the last slide. Okay. I am on full screen, except that I don't see myself. Can I see myself also? Is it possible?
Sir, we are able to see you.
Yeah, I am not able to see me.
We are able to see you and slides both.
Okay, right. Okay, let's continue with that. Okay. No, that's fine. You can close me. I don't want to see. I just wanted to check. Okay. Not the cancel. Leave the meeting. Okay, you can see. Oh, sorry. How do I cut off this side window? Okay, let me see whether I can get it. No.
So
you can see the. Huh? No.
Yes, sir.
Okay. Hold on. I just see. Right. Now I can see it. Okay. The topic I am going to cover is some of the work we did If you are not able to hear me, let me know. Okay. Sometimes the network is bad. You please alert me to that, because I'm not able to see you. So I'm just going on with this. This is what we call as metacognitive neural networks. This is what I said. You are all familiar with neural networks, right? So what is metacognition? This is what we want to cover. And I want to cover some of the application also. Mainly, I'll show that. So you know the basic principle of a neural network is essentially trying to emulate the brain function, artificial neural networks, in the sense that suppose we have a lot of data, you train the network over a number of cycles or epochs, and once the training is proper, and you use a trained network to the second phase, what we call, that is where we use it, where testing, we call it training and testing. In the testing phase, if you give an unknown input data, it will do the right thing. It will, if it is a classification problem, it will classify it correctly. If it is approximating problem or prediction problem, it will make the prediction correctly. This is the general idea, right? So essentially, what is involved is what we call as learning. Human beings, we do that, right? As a child, a baby first, you know how the baby grows, right? So it learns to walk and slowly try to understand all that. That is how the brain is functioning. So this is what we try to emulate in a neural network. So we train with the data. Suppose you want to classify whether your fellow has a cancer or not. You train with a lot of data which has both non-cancer fellow and cancer fellow. And if your training is proper, when a new data comes in, we don't know whether it is cancer or not. It should, if your network is doing correctly, it should classify the right class. If it's normal, you should say normal. If it is cancer, it should say cancer. And immediately you get into the problem, right? In the medical, that's an application I'm going to talk. Medical, this is very, very important. I'm not so much worried about the correct classification. Of course, I am worried, but more severe is what you call. I give you an example. Suppose you have a fellow, he doesn't have cancer, but you classify him as with cancer. So the doctor tells him he has a cancer. Okay, so he gets perturbed, all that. So this is one case. The other case is, I'm coming to that. You see this nowadays in the COVID, right? False positive, false negative, this kind of thing. The other fellow has a cancer, but the doctor says he doesn't have cancer. Which case is more serious? The more serious case is the second one. If a fellow has a cancer, and if the doctor or your network or whatever you are doing classifies him as doesn't have a cancer, that's more serious, because that fellow will never bother about it. But by the time he realizes the cancer shows the symptoms, it may be too late. So in medical areas and all, the classification, this is what we call as misclassification, is more important. You don't want to get false, what do you call this? You have all the four cases, right? True positive, true negative, false positive, false negative. So the misclassification is more important, this kind of problem.
Excuse me, sir.
Yeah.
Sir,
Can
I'm
you
very
hear?
sorry to interrupt. Yes, sir, you're
Yeah.
audible. Sir, but I just had a query. Sir, are the slides supposed to be changing? Sir, are you passing through the slides? Because we can only see the first one.
First slide only. Yeah, I am first slide. I am giving a background.
Okay, sir. Okay, sir.
I'm not here
Thank
to
you,
flash
sir.
the slides. I'm here to talk. Okay, I'm trying to give the motivation for metacognition. Yeah, that's
Yes,
fine.
sir. Actually, we had this technical error yesterday, so we were just confirming.
Yeah. No, this good. You give a feedback. Correct. Check it. Please do that. Yeah.
Okay, sir.
Okay.
Thank you, sir. Please continue.
Yeah. So now you get the point, right? Why? Because if a fellow doesn't have cancer and you tell him cancer, he will not keep quiet. He will go to the second doctor, third doctor. second opinion, third opinion, and he will do the test again and find out that he doesn't have cancer. That's fine, except that he gets agitated over a period of time, but eventually he finds out he's all right. But the other case is more serious because he has the cancer, but the doctor says he doesn't have cancer. That case is very severe. So if a fellow has something, you have to correctly say that. Don't give the false hope. He doesn't have that because he will never check. So this is very important. So whenever you do the neural network, you do the classification. A lot of people are talking about classification. I get 99% accuracy, 96% accuracy, all that. That's fine. But I am more interested in misclassification, especially in the medical area. So even if you find very small number, you classify wrongly when that fellow has a disease that's more serious. So this is the point. That's why they have the metrics. You have what sensitivity, specificity, precision. So you have to go through all, and the right way for this classification problems is a confusion matrix. Yeah, the matrix where all these four classes are identified, and by looking at the off diagonal term, I will know how good is it. Okay, so this is all what is being used neural network. So what is metacognition? Okay, let me define that first. You know cognition, right? Or let me talk about learning. Yeah, you have the term called learning, which we understand. We are trying to learn. Suppose I call meta learning. What does it mean? It really means very put it in short. Meta learning means learning about learning. Suppose you are doing a learning. So during the learning process itself, you evaluate yourself, how much you know, how much you don't know, and all that, right? So that is meta learning. Data also, metadata, data. So whenever you put the adjective meta, means learning about learning. So if I extrapolate here, cognition, metacognition. Metacognition is cognition about cognition. So immediately you see here, it is a kind of hierarchical. You are going to one higher level. So I'm trying to put intelligence into the machines, correct? It is not that the machine is learning, but how does it learn? I'm also trying to learn about the learning process. So whenever I use a neural network to train, correct? Normally that's what blindly do. You get 1,000 samples, you use a network, you train it, right? And finally you test it. But when I do the metacognition, during the training or the learning part, I am also learning how good the learning process is going on. Correct? This is what we always need. And where do you get the idea for this? Of course, it is all involving learning, right? Where do they talk about learning and all? You will be surprised. The discipline is psychology. They have done a lot of studies on this. Learning psychology. Actually, this is learning about learning is what we call as cognitive psychology area. So that's why the computer science people should go across disciplines. You don't think that sociology is irrelevant, zoology is irrelevant. You may get an idea suddenly. So cognitive psychology, they have done a detailed studies how a student learns, and that is very important because we are also faculty. So we also have to know, and if you really understand the philosophy, you bring it, distill that part and bring it to the learning of a neural network. That is metacognition. Okay, don't worry, I will elaborate this in the next slides. Okay, now I am moving to the second slide. You got the intro, right? So very important. The idea is coming from cognitive psychology. So just to do a brief concepts where what points from that discipline is useful. Then I am trying to build it into neural network. Yeah, machine learning. It is not only neural network. You can put this in all systems. Okay, I'll talk about that later. Machine learning, and very specifically on neural network because that's what we were working on. And one specific example I am giving. When I say MC, it is metacognition. RBFN, radial basis function neural classifier, and of course its learning algorithm that we call as PBL, projection based learning. This is what we did some time back. So I want to talk about that, not very detailed, just an idea. I'll give you the references. You can go and do a detailed study, and the software and all that thing are available. That's not a problem. So then the real thing is, I want to show you, of course, whenever you develop a new architecture and new learning algorithm in neural network, you have to compare with benchmark. So that's what you have to do first. And then the application I am showing is in medical informatics. I gave the background, and the area is in neural disorders, mainly Alzheimer's disease. Alzheimer's disease detection using this metacognition, neural classifier, whether you can do better, and some idea about future. This is what I'm going to cover. Okay. Okay. Now let's talk about teaching, right? I'm talking in terms of cognitive psychology. They did a detailed study on that. How do the students learn? See, suppose you are teaching a course in a semester, and when does normally I interact with the students on this, but unfortunately through web I can't do that. When do they prepare for exams? Correct? Suppose you are running a course for an entire semester. When do they really prepare for the exam? A student. The answer is, a student really prepares for the exam 2 weeks before the exam. The whole semester he'll be running around goofing and all. Of course, if you have test and all, he will do that. We will come to that later, but real preparation for the exam is 2 weeks before. And a smart student, how does he prepare? There are regular students who prepare every day, but I'm seeing a lot of the fellows. Smart student is, what he does is, he doesn't spend time reading. He goes to the hostel, picks the fellow who reads regularly, and picks his brain for 2 hours. Arey Baba, you explain this topic to me, and he gets the other fellow to explain. And then when he comes and writes the exam, this fellow who did this for that last 1 week, he gets more grades than the other fellow who was doing regular. This is what I call a smart student. So what is his characteristic? Essentially, what happened? It's gone here, right? Yeah. Essentially, he knows, right, when to study. Sorry. Can you see these slides? Yeah. He knows when to study, what to study, and how to study. This is what they found. So this is what I call self-regulated learning. The fellow is smart learner. So now you see the bullets here. He sets his plan. Plan means when to study. Identify what to study. Suppose some of the material he knows, he won't spend time on that. The one he doesn't know, he will ask. And also, how do you know whether you have learned it? I said learning about learning, right? How do you know? You take the previous exam papers and try to answer. That's what they do. See, this IIT entrance exam and all, they take last 5 years, 10 years exam and crack it. Correct? Of course, every year the questions are different, but if you're trained for that to within the time, that helps a lot. So essentially, this is that thing. Of course, not all students are like this, but some of the smart students are like that. So that characteristic, you set your own goal, plan, right? When do you want to study? What to learn? Go to the other students and learn, and also get an estimate of your how far you have learned. Of course, you can do it during the semester itself, right? That is the idea of your midterm quizzes and all that. So if you look at the bottom, I have given the papers. So this is very heavily researched area in cognitive psychology, learning psychology, how people learn. If you can get some of those ideas into the network, that will be very efficient. Okay, so of course this is the definition. Okay, you can read this. One can the very important. There are 4 concepts: monitor, regulate, and direct. You monitor your learning, and if something is not known, you try to, why is this going like this? I suddenly shifting like this. Okay, control your learning process and direct them with a desired goal. This is general definition, and you look at this. So essentially, the self-regulation is defined as a problem solving. You see there are 4 points here: plan and execute and monitor the progress and manage it. Manage means if you don't know some subject, you spend more time on that. If you know already, you don't spend time on that. And finally, do your evaluation, which is a feedback. That means you take the previous year's papers and try to answer that. That will tell you which subject, which part of the subject you know well, which part you have to put more time. So this is what they have done, studies in psychology. Okay, so actually this is what they have done, collaboration also. That's what our students do, collaborative learning. So 3 fellows put a joint study and try to do. The smart one gets more marks than the other fellows who are regular. So essentially this is the idea of I talked about learning, but similar things is in cognition also. Yeah, when you are trying to learn, you monitor your learning process and plan and control that in proper way to achieve both this process. Okay, is there any way I can stop this? It's coming in between. Okay, the real point is, I'm coming to the point here, learning. How to learn is what we know. Really the question you have to ask, when to learn and what to learn. Say suppose you have 1,000 samples of data, you are using it to train a neural network. If I bring this concept in neural network, the first question I will ask, do I have to learn all the samples? Because I already know some of the knowledge, right? So why do I need to learn all the samples if I already know what is inside the sample? Okay, that's the point. What to learn. So most of the time, the application is enormous. Immediately you see this application is in big data. You are getting a lot of data. Do you really need to learn all the data? No. Most of the time you find the essential part will be around 40%, 50%. All the other 50% is redundant. So this is one of the important area where this can go in a big way and help you to do the reduce the data also which you want to learn. And when to learn, correct? Okay, there are, I'm going into the learning part of the neural network indirectly. When to learn means, suppose you assume, we normally do this in sequential learning. The data is coming in a continuous stream, and sequential learning is you see the data only once and you learn it. After that, it is discarded. It is not stored. So whatever is important, this is what online learning, sequential learning. So in this, if you see, when to learn, what are the possibilities? One sample, suppose I'm seeing a sample, but I check whether the sample is new. Is there any novelty in the sample? If the novelty is not there, why should I learn? I already know it. Discard, delete it. That's the first option. Second option, the sample completely new. I don't know that. The network doesn't know that, right? So I have to learn. Very clear. We do that. Students do that. If some other topics are not clear, he spends more time to get it. Same idea. So in the learning itself, there are 2 possibilities. If it is completely new, you have never seen this before, you can learn it by adding that as a neuron. You grow the structure. But it is not that new, but it is slightly new than what you have. So you adjust the parameters. There are 2 strategies. You grow the network to absorb the new knowledge, or you are closer to it, but by adjusting the existing parameters without growing a neuron, you can learn that. That is possibility. You have to learn. You don't have to learn. And the third sample, always there is a sample. You don't know whether you have to learn or not learn. You see, this is what I say. This topic I'm familiar. It looks like familiar, but not that strong familiar. So you get most of the time cases like that, right? So in that case, you are not clear whether to drop it or whether to learn this, right? So if you get confused like that, like fuzzy, if you get confused like that, essentially what we are saying is you keep it in the reserve, finish all the other samples and come back to that sample. We do that all the time. Whatever was not clear at that time may be clear later. If some topic is not clear, we don't spend, and it needs a lot of time. I don't spend the time now. I finish all the other topics and come back to that later. So essentially that's what I'm saying. Keep it in the reserve. Reserve means not discard. And once you have finished the other part of the learning, come back and check it. Whatever was not clear earlier may become clear now. So this is very important. This helps promote deep learning. The deep learning is not in our deep learning neural network and all. No, I'm saying the quality of learning, deep learning. See, most of the time, this is what our students, most of the time they do that. They prepare for the exam. Learning is not for preparing for the exam. You have to understand the subject. So that's very important. This gives an insight. So that is what we are highlighting here. So assessment, you also have to periodically assess, right? I said that. Suppose you are learning, you stop at that point and give you a problem and check whether you can do that. So this is another thing, right? So this is called in the process of metacognition. Higher level, building more, you can immediately see learning is at the base level. It is meta learning or metacognition at the base level. Metacognition is a higher level. This is what it is. Okay, they have proposed a model. This paper is a classic paper, Nelson and Narain in cognitive psychology. I have given the reference here. You see here. I don't know whether you can see my this thing. Object level and meta level. This is always there, right? Hierarchy. Object level you learn and you monitor, right? You see this process monitoring, and based on the meta level you decide and try to do some action, which is control. There is a feedback mechanism here. Cognitive component is just learning the knowledge, represent the knowledge. Metacognition, how far you are learning. It's a dynamic model of the cognitive component. Are you learning all the things, or some of the things are this thing? How do you monitor this? There are signals for this, monetary signals, inform about the cognition, and control is, yeah, you can see initiate for learning if it is new, or if you already knew it, terminate it, don't continue, or if it is not clear, you reserve it and come back. Now you see the idea. So you are getting an assessment of your learning during the learning process and taking corrective actions. Yeah. Any question? No. Are you able to hear? See this?
Yes, sir,
Hello?
we are able to hear. Sir, we are able to hear. Okay, please.
Okay, no problem. So this is the idea, this coming from psychology. Now I am going to incorporate this in neural network. Okay, so the idea is same, right? You can see the psychology part is the left side. I'm converting the network. Cognitive component I am putting here, right? It's a neural network. In this case, I'm using simple radial basis function neural network. You give the data, I learn, right? But I'm not learning blindly. During that time, I am also measuring how far I am learning, and based on that, I do some correction. This is the monitoring part. This is the control part. Okay, that's how human beings do this. Okay, then how do I put this? Now you compare both the things. Okay, cognitive component. Essentially, you have to select a structure and parameter. Okay, metacognitive, what to learn? Yeah, when to learn, how to learn. Currently, most of the work is how to learn. You give a data, you learn. You never ask this question whether I have to learn this or not. You also never ask the question when to learn. Okay, so these questions during the learning process, hold on for a minute. During the learning process itself, you ask, okay, that is metacognition, one level higher. Now you can see here, this can be on any system. Don't think it is only on neural network. In any mission intelligence, it can come at the top level. It can be a neural network. It can be a neurofuzzy system. It can be a complex value neural network. We have done this work in all these areas. And it can be any machine which is learning. And at top of that learning machine, you can bring metacognition. We have done very recently on clustering. How to improve the normal clustering. Fuzzy C means clustering with metacognition concept. If you are doing something which is the cognitive component, base level, you can bring metacognition at a higher level and try to make it a smart learner. That is the main point. Okay, any questions up to this? Can I continue?
Yes,
okay.
sir.
So these are all the papers. Okay, you can see this neural network is these areas, neurofuzzy system, complex valued. Why complex valued? Complex valued is another area of research. We have done it, a lot of work in this, where normally when you talk about signals, especially in communication, signal processing and all areas, people always talk about magnitude. They never talk about phase. But phase is very, very important in communication and signal processing. Okay, and a neural network, if you're trying to approximate, you approximate only the magnitude, right? Earlier real value networks, but complex, you approximate both the magnitude and the phase. Phase approximation is very important, and it's not easy. No, that's what we have done, and the application is enormous. Communication systems, beamforming system, array processing, signal processing, every area. So that is a different topic. So you can bring this metacognitive learning in all these areas. Okay, that's what I'm saying. Don't think it is only for neural network. Suppose you are having a optimization, you can bring metacognition in the optimization itself. When you are trying to optimize, can you do it more efficiently? That's another part. Okay, so these are all possible, and I talk about only one classic case. The paper appeared in 2013. RBF network. I am not going into the detail. I am giving the reference. What I will do is later I will make a copy of the slides and send it to Madam Dipali. You can, she can circulate to the participants. No problem. Okay. So
Yes, sir,
essentially,
I will.
I'm using. Yeah. Okay. Is it okay?
I
Madam?
will, sir. Yes, sir, I will
Yeah.
circulate it.
Okay. They can. All the references are there. And essentially, I'm talking about a simple structure RBF network. And then how do I bring metacognition learning and algorithm, and I'll show you the benefits. Okay, this is the system. You can see this is what we do normally, right? This is the cognitive component. You get the training samples. This is a radial basis function network, so exponential, correct? Input weights are 1 here. Output weights are the one you determine, and this is the output. I am talking about classification problem. So you classify and indicate the class label. If you are doing approximation, you form the error and send it for updating that. This is very convenient in the sense, this not only the network, I can grow the neurons also. Sequential learning, I start from 0 neuron and go on learning. So the data dictates the structure. I don't assume the structure. We have done a lot of work on that, growing and pruning. So this is very easy to do that. Radial basis function, the great thing is locally supported structure. So that means after some time you find this neuron is not producing anything, you can delete without affecting the others. In MLP, you can't do that. So this is the basic thing. Now I bring the concept of metacognition. This block is metacognition. So it has a monitoring part and control part. Okay. So what is the monitoring part? I just take the same network. I get the signals from here. What are the monitoring signals? Whether the estimated class label is the correct class label, and another is the hinge error. we use a loss function, hinge loss function, and take the error and class-wise significance. Some measures, metrics. Based on that, I decide. This is the control strategy. You see here, whether the network knows already the data here, why should it learn? You can delete the sample. Okay, it is completely new. There are two options. I can add that sample itself as a neuron here, so neuron growth, or if it is not that great novelty there, I can adjust these parameters, which is the second case. Sorry. The third case is I'm not sure whether it is new or completely I know, I reserve the sample. So you are controlling the learning process at a higher level, and based on that you decide. Okay. And so the cognitive component is what we do, how to learn. That's what we do. This does what to learn, when to learn. That is metacognition. Okay, this is a standard thing I explained already. The RBF network, you can say that the input layer is linear, all are one. Output is the thing we want. You can come up with all these things, and the great advantage why we select is we don't assume the structure, the data. Depending on that, we grow the neurons and prune the neurons. Structure is dictated by the data. That's an advantage here. So the signal I said monitoring, predicted class label, you can calculate the posterior probability, you can calculate the error, and you can calculate this. These four measures are used to evaluate the learning. Okay, if they are all, if this predicted and actual class label is correct, it's doing a good job. Correct. So if all is satisfied, that means you already know the sample. Why do you want to learn? You can discard it. Based on that, you can decide. So this is the control signal. Yeah, I mentioned. And if it is completely new, you ask the question. You have to learn. There are three options. If it is already new, add a new neuron. If it is not, you update the parameters. And if the neuron is not being used after some time, see here, I go back here. See, you have learned it in the beginning, but later the output of this neuron is 0 all the time. Why do you want to keep this? Because you remember we are doing online learning. The structure should be as compact as possible all the time. So that is the thing. And so what happens if you delete this neuron and later a sample from that comes in, it will learn again. This is how we do that, human beings. If you've forgotten some topic after 10 years, suddenly something comes, you go back and refresh, right? Your neurons are growing and pruning. So bring it into the computer architecture. You can do a very efficient one. Sample reserve strategy. This is the case, don't know case or don't care strategy. See, normally you have binary, right? Yes or no. But there is a third category, don't know. So those category, you reserve it, finish the other samples to learn, and come back to that later, you may know it. If it is not, you learn again. This is going on again. Okay, is that clear? So of course we have done the learning algorithm. So this is what I said, evolving learning. Evolving means structure is evolving, and we are using in classification problem. We use a nonlinear error function. Yeah, any question? Hinge loss function. If you are not familiar, you please take time to look at it. This is more better for classification. And yeah, these are all the ideas about metacognition. I will not spend time here. I will go to the, what happened? Hello? Can you hear me? Can you see the slide? No. Here. Suddenly this comes on. That is a problem. Okay. System. Okay. So this is the basic algorithm. I will leave the details. Essentially, it's a single step. There is no iteration here. It is for sequential learning. In one shot you learn. The optimal weights you have to find. The equations are shown here, and it can be shown it exists. So this is why it's called projection based learning. It does it very fast, and sequential learning. Okay, I will not get into the details of this. So you can see the more or less a pseudocode of that. We start the network to grow. These are the signal, essentially significance of the sample with all the measures, and then based on the significance we decide the strategy. This is the control. This is what we do normally. We bring the metacognition at the higher level. Okay, so when I do that, you are becoming a smart learner. That's the idea. Okay, so smart learner, immediately you can see okay, so immediately I had to do BCI, right? I mean benchmark, UCI. Okay, the data details and all given in this paper. I'll give that. The three problems we selected. One other point I want to highlight here, you look at the number of samples. Of course, it's not impact factor, it is the imbalance factor. There is an error here. But you look at the samples here. Training samples is 210, 200, 100. If I use metacognition, question is, do I have to use all the 210? Answer is no. You will find it. You will see only 50% of the data is needed. Okay, you can see that in the next slide. We are compared with the other classifier, SVM. SRN is another one. But you look at this column, NU. NU is the number of samples used. Okay, so IS is image segmentation. You can see 210. You immediately see here number of samples 89. You see the accuracies 94, 94. Overall accuracy, average accuracy is far better than the others. Number of samples used is 89 out of 210, 50%. You can see the implications in big data right away, and similar results for the other ones also. More difficult problem, liver disorder, ionosphere, 200, 100. Okay, you can see 116, 58. So you get, it is not that all the samples are needed to improve the accuracy. No, right samples are important. How do you determine right samples? Putting metacognition in the learning process, you eliminate redundant samples automatically. That's what it does. Okay, so of course you can say K is the number of neurons. You can see that if I use SRAN is another learning algorithm, 47, but SVM, number of support vectors, you see the network is compact. Network uses 50% of the data and does better than the other things. Okay, that's the idea. This is what we call smart learning. Okay, any questions here before I get in? I mean, these are all for all the other data. Okay, these are all standard thing. You can see the thing, all the things we have compared, and the bold items is the result, and the number of samples used also is here, because this is done over a 10 random trial. That's why the mean is given, mean and the deviation, standard deviation is given. Complete thing is there. You can refer to this paper here. All the data is there. My colleagues, we did this. Okay, so I'm going to close here with this before I get into the next topic. I mean the next application. So really, putting metacognition improves the learning, and this is what we do. Sample reserve.
Sorry, sir, I have a selecting this support vector. Yeah. I have a question from the previous slide. How we are deciding the support vector?
Yeah, trial and error only, right? What is, you are trying to optimize the support vector? You know, this is a very standard package. LibSVM, okay. You can take, give a maximum number, it will fix it. You look
Right.
at the paper. All the details are here. The paper. I will
Okay,
send
sir.
it.
Thank you.
Yeah, I will send it.
Sir,
No problem.
sir,
Yeah.
I have
Yeah. Go ahead.
one query, but it is somewhat different from the topic. It is on learning only, but
Yeah. Go ahead.
sir, if a person, I want to ask that one person can learn distinct learning in the same period, distinct type of learning in distinct areas.
Yeah. You can. You can. Yes. Yes. That's how we study 6 subjects in one class, right?
Yes, sir.
Yeah. Because the data is different, right? So let me illustrate. See, your brain has a lot of neurons, right? So different subjects, different neurons and different connections are set up in the brain.
Sir, is
Another
there any condition that they get mixed up?
No, never mixed up. Actually, the other concept is, if you learn one subject, can you use that knowledge in learning another subject? They say that all the time for language, right? If you learn one language, suppose I learn Sanskrit, can I learn Hindi easier? Of course, yes, it is easier. But can I learn Tamil? That's difficult. Correct?
So when it comes for the courses, different courses.
Yeah, I'll tell you. See, if you take communication has a lot of maths. So that is why
Yes,
they
sir.
always ask you to do maths. Without maths, you can't do anything. Maths is the queen
Yes.
of all sciences. Very fundamental. I mean, you can have physics, maths, you can cover the most of the thing, right? So this is what we call as transfer learning. If you learn one topic or one domain, can you transfer that knowledge or experience to another domain? Very hot topic in machine learning now. Okay.
Okay.
All these are questions. Yeah. Okay. Let me go ahead and finish it. Then we will have an open discussion. Okay. Very important. Yeah. Human beings, without any effort, they do this. But to do that with the machines, that is research now. Okay. So, okay. This is what I'm going to talk. Very quickly, I will finish. I don't have much time, 15 minutes. So, this is done by my student. Actually, he is from Mysore. His name is Mahanand. And he has done a lot more work after this. I'm giving the basic thing long time back. Anyhow, we will discuss this. Essentially, because this may be of interest to all of you, computer science people, don't say that you want to do research in image processing. Image processing area where everything has been beaten down to death. Do something in an interdisciplinary area. Very useful area is medical image processing. Combine the disciplines together, medicine or medical image and image processing. If you combine, you get a lot of insight and brings a lot of value to society. Yeah, the people's health is very important. So one of the important area is Alzheimer's disease. Whether I can use MRI, magnetic resonance image, to predict or classify. The simple question is classify. Prediction comes later. For doing prediction, you need the data over a period of time. We don't have that. So if you can collect the data over a time, and you can do a prediction whether this fellow is susceptible to get AD or not. That's an important question in medical. What we do now is, you take MRI image and you want to find out whether this fellow is starting or what stage he is in Alzheimer's disease. You know Alzheimer's disease, right? You become like a child, okay? Some general statistics you can see here. This is also becoming an important problem now. It is progressive. Memory loss, poor judgment. People become very old. People become like children. They don't know. There is no single cause and no cure. Slowly it is coming. Very recently I saw them. They have identified the gene, but I don't know. Now you can see the composition. Alzheimer's disease in the world is a big problem, 65%. And people are getting old and lifespan is increasing. likely chance of more getting into this kind of problem. So, okay. So what are the testing methods now? Essentially, they do the test. They ask you to walk straight, turn right, turn left, and come back. People get stuck. They don't know what to do. These are all correct. If you talk to your doctor, they will tell you, and they give you a score. So very, very subjective. Most of the time, the person suffering this don't understand what you are asking itself. Okay. So this is what the final point I put, CDR, clinical dementia rating. They give a number 4.5 up to 10, I think. If you're above something, then you have, if you're below something, very subjective, lot of problem. Question is whether we can do this non-invasive. Okay, there are a number of imaging methods, right? You have PET, you have CT, you have MRI. Okay, people can work with other areas, but we looked at MRI. Okay, whether from MRI you can identify. Why MRI? You can see the thing here, and not only MRI, we can go further with the functional MRI, fMRI. Yeah. So, and the thing is, you don't ask the subject to do anything, right? You just ask him to get a scan of his brain with MRI, and that's very easy, no problem. Okay. Okay. Then how do they identify with MRI? Let's see. So is there a data? Yes, number of data is there. Big initiative. The early one is what is called OSIS. If you are working in that area, you know, but that is not very broad based. So they have recently, not recently, some time back started. If you're working in AD, you should be using ADNI. This one, ADNI data, right? Across different hospitals, very systematically. This is very difficult process. So this is available. You do a Google ADNI, you will get that. OSIS, you will get. You want to work on that, and already published results also there. You have to put in ADNI and acknowledge that it is available. And we are trying to develop something in India also. Since you are in Delhi, National Neuroscience Institute Delhi is very active in this kind of work. You should talk to them. You can get the data, and Indian patients is very important. We have not got that benchmark, because okay, why this is important is this is important. How do we detect with MRI? See, the brain matter consists of three things, right? Gray cells, white matter, and then the fluid. So they say a person affected with AD will have lesser volume of the white matter. What is that? Yeah, gray cells. The volume will be smaller. It gets reduced. So normally you do an image with a pixel, right? Pixel based analysis. No, here you have to use it voxel based, because volumetric morphometry, this is called VBM. Okay, what they do is they take the original MRI, do all this pre-processing correction, unified segmentation, smoothing with a kernel, and smooth thing, then you do a statistical answer. You can't do an individual. They always do a group study, because the brain is not same in everybody. Is another point. The brain shape is different for different people, so yeah, group wise analysis is important here. Okay, so you have to extract the future from this, and this all this, see, I showed the process, right? The results of that is shown here. MRI is the raw data. This is the segmented, smooth, and then from the VBM you find maximum intensity projections where the differences are. Of course, the brain, they have three views: axial, sagittal, and top view. That's why you get the three pictures of that: front view, side view, plan view, something like that. So you have to talk to doctors and work with doctors on this, try to do this. Okay, so then you have to convert, right? What is the study? So we studied the complete data, right? Of course, you can, very important, age is important, gender is important. Okay, so how do you select the futures? All the details are there, future, and then we did the analysis, right? Training, and just compare the performance, and you show here accuracy. You can see here, this is the other part, sensitivity, specificity during testing. Actually, you see here, if you do the, if you do that with all the futures 19,000, your accuracy is 76, but with the reduction, recursive future elimination, you can get a better accuracy. All the redundancies is removed, all that is, you can get a good accuracy here, 84%. So that is not very critical, but what is more important is you can go back and identify the regions, affected in the brain. So these are the regions where the volumetric, the gray cells are smaller. So definitely this is a AD patient. And then it's not only important to that, this is how you should do the research. Okay, you can identify this region, but what is more important is what the region is responsible for functions. Okay, that is very important. So they say this, these are all brain terms, right? Insula, all that is thing. And then we did the analysis. Okay, okay, this is our main summary of the conclusions. Okay, now you can see in the age group 60 to 69, sound processing, hearing is the problem. I'm not saying here that if you have any grandfather in the 69th year and he is saying he is very hard of hearing, don't say he is suffering from AD. This is likely, that's what we are saying here. Degradation, slow process, that's a good indication. 70 to 79, memory related problems. It doesn't know, forgets all that, right? So you see the bottom part is the region. We identify the region and we are identifying the region for the function, and that will show as the outside. 70 to 79 and 80 to 89, everything is a problem. This is how the AD progresses. So at 60 to 65, 69, if somebody is saying they are not able to hear, they can't follow you and all, early indication of AD. Okay, so again related to male and female, I'll close it, very short thing. This it's going okay. Emotion related problems, male, whereas in females it is mainly memory related problems. That study also we have done. You can do a complete study and identify and all that. Okay, so to close, okay, it's not only for AD, we have done it, we have gone further. Alzheimer's disease was the starting point. We have done it for autism. Autism affected boys, right? Students, early age, autistic child. Then we have gone further. We have also done it for ADHD. ADHD means attention deficit hyperactive syndrome. That is hyperactive kids, you know, all that. Anything affecting the brain, neural disorders. Of course, Parkinson's disease. We are trying to work on dementia. All these areas are very important. Okay. So plenty of things, degenerative disease. MRI only we have done. You can take it from other data also, CT. You can combine with gene data also. All kind of things you can do. Okay, so these are the papers. Okay, the first one is for Alzheimer's disease, and more I have given inside. And Mahanand is the student, and he did his work and his thing. He went to Harvard as a Raman fellow for postdoc. Did a lot of work there. You can search Google in his name, you will get all the relevant papers. And the other one, Vignesh, is the one who did autism. We are still working on that. A lot of work is there in that area also. And we have used fMRI also. ADHD, autism. Okay. So these are all this thing, right? I want to close. I said we have done for real valued, right? This is the real valued. Okay. So these are the papers I already gave that. We have extended this to complex values where signals are complex, correct? And for neurofuzzy systems also. Okay. And in medical informatics, I said AD, we have done Parkinson, we have done autism, we have done ADHD. Okay. Another area, video analytics, human action recognition. Action recognition is very important, right? From video. And where complex value signal processing, where adaptive beamforming, QM equalization, all this, where signals are complex and you have to do the processing in complex domain. Okay. Current work is static, right? Then the second part is very important. For human beings, common sense, right? How do you bring common sense into your learning neural network? And you have the other one, introspective, retrospective. So we are going close to psychology here. Social learning. How do you do collaborative learning? Students do all the time, right? 4 students get together and prepare for the exam. How do you get 4 neural networks to do this? This is what somebody asked. Transfer learning, right? Transfer knowledge from one domain to other. Of course, related disciplines is somewhat okay, but completely unrelated discipline, will it help? Yeah, open questions. But I feel it will help. Some level it will help. Okay, so these are all the open problems. And I want to close. I think I overran 5 minutes. So I will close and open up for questions. Any questions? I will keep the slides in the side.
Thank you, sir.
If you want to ask, the time for the question is up to you. I am free. Okay, madam, you can take over.
Thank you, sir, for taking time out of your busy schedule to deliver such an insightful and knowledgeable session. We have a couple of questions.
Yeah, please go ahead.
The first one is, how to choose between deep and shallow neural networks? Is it related to the application we are handling?
No, shallow. See, if you see all the work I have done here is not deep network at all. We try to get. Hello, somebody is unmute. Okay, we are trying to learn the basic concepts, right? So if I understand this, then you can go ahead and do a deep learning. My suggestion is don't, because one of the important problem with the neural network learning is it learns, right? Deep learning, deep network learns. But if you ask the question, why does it learn like that? If it is doing a classification, that's fine. It gives 99% accuracy. But why it does that? What characteristic is important? What is not important? That is missing. Correct? Give an explanation for learning that classification rule, because it's a black box. So try to do that in simple network, and then you real problem you want to crank out where you can get more explanation, you will go. That's my recommendation. See, a lot of people use the toolbox and do blindly. No, never do that. Understand why it is doing like that, and then try to do it. Your understanding and solution of the problem will be more clear. Yeah.
Okay, thank you, sir. So the second question is, what is the best approach to understand on what features the deep neural network is working on? Or is it that the feature reduction and extraction part is completely abstracted from the user?
That is what I said. Which feature is important? Why it is classifying like that? We don't know that. See, interpretation of a neural network learning classification is still missing. Very hot area. A lot of people are working on that. See, your neural network does the classification, right? But you have to give the explanation why it does that classification. What feature is important, what are not important. In quantitative terms, not in a black box form.
Okay, sir.
Deep network, right? You have convolution layer, pooling layer, all that thing. Which one is important? Why it is doing like that? If you have an image, overall it gives 100%, 99%. If you leave out some, what is the effect? We don't know. See,
Okay, sir.
most of you don't blindly do the deep network. You can do that, that's fine. But ask the question why it is doing like that. What is the reason behind this? Any problem? Okay.
Okay, sir. So we have another question. How is the effectiveness of metacognitive networks measured?
Okay. I showed you. I showed you that slide, right? Okay. Let me go back to that slide. I showed you. Sorry. Hold on for a minute. Here. Here you can see that slide, right? I'm talking about accuracy, structure of the network, neurons, and number of samples used. That is the indication. NU, out of 289 samples are used. Network size is 50 neurons. Accuracy, compact network with higher accuracy with lesser number of samples used. That is an indication. Okay?
Yes, sir. Thank you.
Yeah.
Thank you, sir, for today's session. I'm sure each one of us has something to take away from your words.
I
would now request.
Any question or any comment?
No, the topic was really very interesting. The topic was really interesting.
No.
I myself is working in this field. I'm also working in the field of AD, but I'm using EEG signals, not MRI pictures. I'm working on EEG
madam,
signals.
Yes, madam. This is what I say. You can use EEG signal. You combine with MRI, combine with fMRI.
Yes, sir.
And
But I got a very good idea. But through your lecture, I got very good idea that I can combine these MRI images of brains and EEG signals both and can find a predefined area from where we can get that particular problem part.
Yeah. See, I want to tell you, solving the problem is important. Whatever tools necessary, use it. You can combine both.
Yes,
your insight will be more better. See, the thing is, when we collect this data, if you take image and the voxels, if you take, it's all in 15,000, 20,000 and all. Do you need all that, right? If you take that as the futures, answer is no. That is where the metacognition and this concept becomes important. So that is why we have done EEG.
I am combining. I am combining EEG signals with some question array. I have taken a question array. I have asked some questions and taken the answers from the person and combining that with EEG signals, we are trying to predict. Predict at earlier stages.
Yeah, EEG signal is still more difficult because it is non-stationary.
Yes.
And the person time also is important. If the same person you take
EEG
different times, it will be quite different. Yeah.
Exactly, sir. Yeah, exactly. Under stress, they are coming different values. Under normal life, they are coming different values, and from that to take a mean value is very difficult. From that.
Yeah, you can combine MRI with EEG to say more clearly.
Yeah.
That is possible.
Yes, sir. I have got a very good. Yes, sir. I have got a very good idea from these slides. I will just try to study the papers, and I will just talk to you how I can incorporate these two works together. I will get.
Madam,
yes, sir.
I will put you in touch with Mahanand. He is in Mysore faculty. He is doing a lot of work in this area. He is also talking to neuroscience people and all. So he can really help you. Yeah. The only point I want to close.
I will take.
Only point I want to close is metacognition. The idea don't think it is only in neural network. That's what I wanted to say. In any area of research you are
Yes, sir.
doing, whether it is fuzzy systems, optimization, or even anything you do, machine learning or machine intelligence kind of thing, you can bring that concept at a higher level to do it more efficiently. That's all. Try to
Yes,
approach
sir.
like that. Power
I
system people can use
I
it.
will take his
Power,
number.
yeah, power system.
Yes, sir. I will take
Saying,
his number from you and I will just contact the person.
yeah,
How
I'll
the
send you
these
the.
things can be combined together.
Actually, he was selected as a Raman Fellow to spend 1 year in postdoctoral
Okay.
fellow, Harvard Medical School.
Mm-hmm.
You can do a Google search, Mahanand.
Okay.
All his papers will come. Yeah.
Okay. Yeah. 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 I will do, sir. I will definitely. Okay. Thank you, sir.
Okay. Thank
Thanks
you.
a lot for the wonderful
Thank you very
session.
much for suffering me for one hour.
No, no, sir. It was 1 hour. I think was very less to listen. Your words, your knowledgeable words. Palak,
Okay.
can you invite Dr. Raji?
Yes, ma'am. I would now request Dr. Rajiv R.R., Program Head, International Center for Free and Open Source Software, to kindly deliver the vote of thanks.
Okay, thank you,
Good
ma'am.
evening, sir.
Good evening, sir.
Good evening.
Namaskar.
Good evening. Yeah. So I can
Yeah.
speak in Malayalam also.
Whoa, good.
I
Okay.
was in Trivandrum for 20 years. I worked with Dr. Kalam, SLV.
Oh, okay. You are staying in Karakutam or in Trivandrum city?
I was right in Padmanagar, Padavangadi, Purathe.
Oh, okay. In the heart of the city. Okay.
Okay. Yeah. So,
Okay, sir.
Sir, Rajiv sir,
Yeah.
IC Force program, and this webinar is in the collaboration with IC Force and BPIT.
yeah, I saw that. Yeah.
Yeah. Okay.
Yeah.
Okay.
Yeah, Rajiv sir, please.
Thank you. Yeah.
Okay, sir. Your session was really wonderful. Then because especially in some, medical imaging kind of things, then also some of the insights to give into that area, and also the neural network, how to apply these things to the kind of the things. Then formally, I just going to express my sincere gratitude on behalf of IC Force to you, sir, for
Thank
a
you.
wonderful session. Uh, then some of the things related to this one also. Actually, most of the persons working in this area is proprietary, using mainly using the proprietary softwares, not the very few persons working in the open source technology. That is, I found that is the things identified in this area. But nowadays, a lot of research is coming with the open source technology kind of things. Then, first of all and foremost, I thank our chief guest and resource person, Professor N. Sundararajan, retired professor, Electrical and Electronics Engineering Department, NTU Singapore, for having such a wonderful sessions on metacognitive neural networks. Then we are really enlightened with your knowledge and presence, sir. And also we are thankful to all our supports of BPIT, especially the persons from the Department of Computer Science and the FOSL, and also my team. My team means IC Force team, for all their enthusiastic support to make this webinar a great success. Then today is our third day, then 2 more days in front of us. And also the special thanks to my fellow colleagues from BPIT and all those in the organizing committee, and also the IT support team and administrative team of IC Force, and the Fossil family for their endless support and coordinations. And also our heartfelt thanks to our participants present here for the active participations with a lot of questions. That means in between the sir permits participants asking questions in between the sessions also. That's why it's a very active participations from our participants. Then we move to the end of the today's webinar and expect all your presence in our future webinar sessions as well. Last but not least, I thank you, my friends, for your cooperation in making this session is a resounding one. Thank you. Thank you,
Sir,
sir.
I would like to take this opportunity to thank you, sir. I would like to take the opportunity to thank you to give the opportunity to BPIT to establish the fossil, and we are able to conduct these good webinars. In future, also we'll plan such mega events, and I'm sure that sir sir is always accepting our invitation, and in future also we are going to have a great relationship with him.
Sir, I just want to add a point. I'm retired
Yeah.
now. I'm going to all the universities and colleges, IITs and all, trying to give lectures. Not only the technical sides on how to do research and how to do a good PhD and open source software. You said some of this software is available, open source only. I can put you with the right person. We'll try to develop, because this, especially the voxel-based morphometry, the software and all, that is, if somebody starts to do that, it will be difficult. The student I mentioned, he already talked to some doctors in Chitratirunal also earlier.
Yeah.
So we started some projects with that. So maybe you can give me a push for that and try to develop these tools, which makes this MRI, fMRI processing easier. Yeah.
Yes. The real thing behind this one is the multinational companies actually doing this type of research, because that is why they are applying for the patent kind of the things. That is why that thing is not available.
Yeah.
That's not available in the open source.
Nice to meet you, sir. Nice to meet you. We'll be
Yeah.
in touch.
Awesome. Yeah, definitely, sir.
Thanks, sir.
Thank
Thank
you.
you,
Sir, you
Sundararajan,
are
sir.
available
Thanks a
to
lot
Trivandrum
for
or
sparing.
I am in
Singapore, sir?
Bangalore. No, I'm in
Okay.
Bangalore. I come to
Oh,
Trivandrum very often. So
okay.
you have my email. It's
Yes.
just emsundara@gmail.com. You can send a mail.
Yeah,
Okay.
definitely, sir.
Okay.
Okay, thank you. Thank you, sir.
Thank you, Deepali madam. We will be in touch.
Thank you, sir.
Bye.
Thanks a lot. Thank you. Thank you, sir. Okay. Namaskar. Good evening.
Okay. Namaste.
Okay. Thank you, Rajiv, sir. Okay, sir. Good night.
Okay,
night.
good night. Too.
Participants, feedback form is there in the chat window. You can fill the feedback form for the certificates. Thank you. Okay, sir.